Last time we finished a quantitative description of the Deuteron intermediate reacting to helium-4 and trace tritium and neutrons. Now we need to describe the chemical environment around the intermediate diffraction state and how this state forms from molecular D2. Molecular D2 has now been shown to form at palladium vacancies by several researchers using molecular modeling. Given molecular D2, we need to describe the transition to the deuteron fusion intermediate state and the factors controlling the transition rate. We will start by outlining the electron states throughout the process shown here, with palladium gas going to palladium solid, to absorption of deuterium, then void formation, molecular D2 forming in the void, which transitions to the fusion intermediate on the way to helium. The various driving forces for the reactions are also shown. For each step, we can assign the valence electrons of palladium and deuterium to their respective orbital states. Palladium gas is shown in the ground state, which when in a solid transitions one electron into the 5s conduction band. With the addition of deuterium in the 1s state, we get palladium-deuterium bonding. The void concentration increases with increasing deuteron concentration, which we will discuss at another time. And molecular D2 will form in these voids with significant bonding between the two deuterons. The transition to the fusion intermediate puts the electrons from the molecular D2 into the 2s conduction band, analogous to the valence electron of lithium, which alloys with palladium. One electron will be held in the diffraction state very close to the two deuterons, similar to the 1s electrons in lithium. But recall that the electron in the transition state bond must be of the conduction band. This electron concentration very near the deuterons is simply the diffraction pattern of the conduction band electrons, much as all metal atoms diffract their conduction band electrons. We can again use the time-dependent two-state analysis to estimate the half-life of the transition of molecular D2 to the fusion intermediate. We have already described the intermediate wave function, and approximate molecular wave functions for D2 are readily available. The wave functions are sketched on the respective potentials for molecular D2 and the intermediate states. This shows the tunneling that must occur, which is the rate-determining step. From the time-dependent analysis using the respective wave functions, we can calculate the reaction half-life as shown here. We see that the 0.76 angstrom separation found in vacuum will give a 10 to the minus 8 second half-life. Note the 10 to the minus 5 second at 0.84 angstrom and the 10 seconds at 1.05 angstroms. To get an idea for why the fusion reaction seems to occur at the surface, we just need to look at molecular modeling done by Olga at Coalescence and reported at ICCF 18. From Olga's work, we can see the most critical factor leading to shorter D2 bond lengths, and hence shorter half-lives, is the location of the original vacancy near the surface. Shown here is a slide from Olga's presentation, and we highlight just the palladium with the bulk separation of 1.05 angstrom and the near surface separation of 0.84 angstrom. Recall that the half-life of 1.05 angstrom was 10 seconds, and of 0.84 angstrom was 10 to the minus 5 seconds, 6 orders of magnitude difference in rate. Next time we will explain why the near-surface vacancies provide for shorter D2 bond lengths and discuss controlling factors for vacancies and the impact on the overall fusion rates.